Welcome to another session of Basic Mathematical Analysis class. Today we will discuss about neighborhoods. It is chapter 11 of your prescribed textbook. So the definition 11.1.1. A neighborhood of a point x belongs to R is any set V that contains a neighborhood epsilon neighborhood V epsilon of x. We have studied about the epsilon neighborhood. So the definition of epsilon neighborhood of a point x, where x belongs to the set of real numbers. That means in your set of real numbers, you can mark your x. Now, from this x, you take epsilon distance to this side and epsilon distance to this side too. So here the point should be x plus epsilon, and here the point should be x minus epsilon, right? So we will say that this one as an epsilon neighborhood of the point x. But here what we are defining is a neighborhood of a point. No need to say that it's an epsilon neighborhood. We will say that it's a neighborhood of the point x. So when we will say that it's a neighborhood, that means suppose you have got a point here and a set. Suppose this is my set V. So when you will say that V is a neighborhood of this point x, the condition is that it should contain an epsilon neighborhood. So here it should contain an epsilon neighborhood. See, a neighborhood of a point x belongs to R is any set V that contains an epsilon neighborhood, that is V epsilon of x equal to x minus epsilon, x plus epsilon of x for some epsilon greater than 0. So when you are taking your real line, you can go for, suppose I am taking the point 0. Now here the point is minus 1, here the point is minus 2, here minus 3. Here I will get it as 1, 2, 3. So my question is, when you are considering V as some closed interval minus 3, 2, will it be a neighborhood of 0? Will it be a neighborhood of 0? I am taken V is equal to closed interval minus 3, 2. Now, will it form a neighborhood of the point 0? So, what we want to check? We want to check for any epsilon, will we get a epsilon neighborhood which completely lie inside your set? Completely lie inside your set V. So, your set V is minus 3 to closed interval, right? Minus 3 to 2. So when you're taking this 0 and I'm fixing my epsilon is equal to 1, what will happen? So 0 plus epsilon 1, right? And 0 minus epsilon, I will get minus 1. So there exists an epsilon neighborhood, right? So even if you can take this epsilon is equal to 1 by 2 also, okay, anyway you will get an epsilon neighborhood which completely lie inside your set V. So closed interval minus 3, 2 is a neighborhood of the point 0. I think now it's clear. The definition is clear, right? Now we will define when you will say that a set is open. A subset G of R is open in R if for each x belongs to G, there exists a neighborhood V of x such that V is contained in G. So we will say that an open set. Okay, so suppose I have got a set over here. This set I am naming as U. So when you will say that this set U is open, condition is that if you took any point of this set, any point of this set, there should exist an open set, there should exist a neighborhood V of this point. Suppose I had to taken this as X, then there should exist an neighborhood V of X such that this V is contained inside this U, right? So a subset G of R is open in R if for each X belongs to G, there exists a neighborhood V of X such that V is contained in G. So I have taken this open set as, instead of U, you can take it as G, because in definition it is given as G. So when I am taking this as G, so this G, I should find a neighborhood. Okay. Now our question is, will this neighborhood, every neighborhood should be open? No need. See, we have already seen that V equal to -3, closed interval -3, 2. This is a closed set, right? So this is not, it's not an open set, but this is a neighborhood. Okay. Now, even though we have not come across formally the definition of a closed set, then also I am saying that this is a closed set because you have studied that it's a closed interval. Okay. With that condition only, I have said that statement. Now we are moving formally to the definition of what is a closed set. So a subset f of R is closed in R if the complement of that set, that is C of f, that is R minus f, is open in R. So what is meaning of closed? So closed means not open. Okay, or this is not a true statement, so we can say that complement is open. Okay, so a set is given, its complement is open means we will say that the set is closed. So when you will say that it is open, if for each point of that set there should exist a neighborhood V of X such that V is completely contained inside the set G. Now, how to show that a set is open? To show that a set G is open, it suffices to show that each point in G has a epsilon neighborhood contained in G. In fact, G is open if and only if for each X belongs to G, there exists epsilon X greater than 0 such that X minus epsilon X, X plus epsilon X is contained in G. Okay, it's a very simple one. So we are dealing with real numbers. So I'm marking here the real line and we have got some points. Okay, so here I'm making the point X and I have given a set from here to here. This set is given as G. I want to check whether this G is open or not. For that, what we have to do? For that, we have to check whether there exists a neighborhood of X. That is, if there exists a V which completely contained inside your G or not. By definition, right? Now, when you will say that V is an neighborhood, we will say that V is a neighborhood whenever, if I Now I have taken this as X. There should exist an epsilon neighborhood, right? So this is my epsilon neighborhood, and this one is my neighborhood. So when I am saying that this set is open means there should exist a neighborhood, right? For existing neighborhood means there should exist a epsilon neighborhood. So instead of saying that there should exist a neighborhood, it is enough to say that whenever a set G is given, if for every x belongs to G, if we can find an epsilon neighborhood which is completely contained inside G, then also the set is open. Can you follow? First of all, we have said that G is open means for every x belongs to G, there should exist a neighborhood of x which completely contain inside G. Now, when you will say that a set V is an neighborhood of x, that means V should contain an epsilon neighborhood of x. So, instead of saying G is an open set, it is enough to say that for each x belongs to G, we can find an epsilon neighborhood of x which completely contain inside G. So this is nothing but the epsilon neighborhood, x minus epsilon and x plus epsilon x. Okay, so which is contained in G. Now how to show that it's closed? That is next question. How to show it is closed? Take its complement, right? To show that a set F subset of R is closed, it suffices to show that each point Y not in F has an epsilon neighborhood disjoint from F. In fact, F is closed if and only if for each Y not in F there exists an epsilon Y greater than 0 such that F intersection Y minus epsilon Y, Y plus epsilon Y is empty. Right? To show that a set is closed. So we want to show that a set is closed. Okay, what should we have to do? We should take a point not in F. So I'm taking a point here Y. This is my set F. I have taken a point Y not in F. Now we want to show that it has a neighborhood, epsilon neighborhood, disjoint from F. So it should lie outside where set F. Now F is closed if and only if for Y not equal to, Y does not belongs to F, there exists an epsilon neighborhood of Y which completely contain inside outside your F. That means your F intersection Y minus epsilon Y comma Y plus epsilon Y should be empty. Can you follow this? See, in your real line, suppose we want to 1, 2, 3, minus 1, minus 2, minus 3 and minus 4. If I am taking 4. Now I am taking the set 1 by 2. My set is 1 by 2 comma 2. Okay, so 1 by 2 means somewhere here it will come. First of all, I am marking my set. So this is my 1 by 2 to 2. So this is my set. Okay. Now I want to check whether this set is closed or not. For that, what we have to do? We should consider a point outside your F. So I am taking a point outside F. That's somewhere here. Okay, maybe minus 1 by 2 or something. So if I'm taking minus 1 by 2, what I should consider? I want to get an epsilon neighborhood of this minus 1 by 2 that will lie outside my f. Will it possible? Yes, right? So I can go for like this, a small epsilon. Okay, so suppose I had taking the set as minus 3 comma minus 2. Open, I'm saying open. So minus 3 minus 2. So this is my points. Okay, here what will happen? Will it be open or closed? Suppose for every x not in this f, we want to check, right? For every y, each point y not belongs to f. So in this case, this is my f. So minus 3 is not in f. So minus 3 does not belongs to f. But if you are going for any epsilon neighborhood of this minus 3, it will have intersection with this f. Am I right? For any neighborhood of epsilon neighborhood of minus 3, it should have non-empty intersection with f. So this condition cannot be existing. That means the set what I considered is not going to be a closed one. It should be open. So this one is open, but this one is closed. So this is the way how we can check whether a given set is open or not. Now we will have some examples. First example is the entire set R is open. So the entire set R is open means we should get for any real number 1, 2, 3, 4, here minus 1, minus 2, minus 3, minus 4. So whatever the point we will take, we want to say that there exists an epsilon neighborhood of that point which completely contain inside your set. Now what is our set? R. Now if you are taking any neighborhood, let me say any neighborhood, we will get this neighborhood is completely contained inside your R. So in particular you can go for epsilon is equal to 1 by 2 or epsilon is equal to 1. Even epsilon is equal to 10 also it will work, right? So when you're finding the neighborhood of 0, we can go for this minus 1, 1, even minus 1 by 2, 1 by 2, even here 0.01, here minus 0.01, it will work. But generally we will say that epsilon is a small quantity. So we are not going to take epsilon is equal to 10 and all. We can take an epsilon, a small quantity itself. So any small quantity for the value of epsilon, this will hold. Our definition will satisfy. So we can say that the entire set R is open. Next example is the set G. G is set of all x belongs to R such that 0 less than x less than 1. What is that set? 0. I'm making here 1. You're making us minus 1. This is minus 2. Suppose if I am extending this, this is 2. Now this is my real line. From here, you're taking from 0 to 1. So this is my set from 0 to 1. So this is my set. Now how it belongs to 0 is not there, 1 is also not there, right? Now if you're taking any point inside of this, can you find an epsilon neighborhood that completely contained inside the set? Suppose I am taking this as x. Okay, this as x. Now suppose I am finding the distance, this is taking as d1 and this distance as d2. So what should be my d1? d1 should be equal to x minus 0, that is x. What should be my d2? d2 should be 1 minus x. Now I'm taking my d as minimum of x comma 1 minus x. Okay, even if we can have 1 by 2 into minimum of x and 1 minus x. Suppose my x is suppose I am taking this x as 0.2. X is equal to 0.2. For getting a specific example only, I am saying x equal to 0.2. So what should be my d? D should be equal to 1 by 2 into minimum of 0.2 comma 1 minus 0.2, that is 0.8. So I'll get 0.2, that is 1 by 2 into 0.2, that is 0.1. Now suppose I am taking this 0.1 on this side and this side also, distance. Can I get an epsilon neighborhood which completely contained inside this set? Yes, of course, right? So like that we can form here epsilon, we can take it as either minimum of x comma 1 minus x, or we can take it as 1 by 2 or 1 by 4, any value which is less than these two. Okay, so minimum of x comma 1 minus x. So we will get an epsilon neighborhood. We specified the epsilon here. So whatever the x you will take, you go for such an epsilon. I will make this as epsilon x since it is depending on x. So this set is open. Next example is any open interval I equal to open interval AB is an open set. You can try, right? Any open interval. So here also I have taken open interval, means the condition should be a less than x less than b, right? Open interval. So again in real line we will get here is a, here is b, means this set. So again what we have to do, what should be, is this is my x, what should be my epsilon x? The same way you can go for minimum of x minus a comma b minus x, right? So fix this as your epsilon x. You can easily see that this set is an open set. Now next is the set closed interval 0, 1. So closed interval 0, 1, this is not an open set. What's the reason? So I should find 0, here is 1, here should be minus 1. So the line is extending like this. Now suppose I am taking a point over here. No problem, you can go for the distance and take the 1 by 2 or the half of that distance, it will work. But suppose I am taking, because 0 is an included point, right? If I am taking this 0, any neighborhood of 0 will have some portion lying outside your set, this side, right? This was your set. So any neighborhood of 0 will have some points lying outside the set. In the same way, when you're taking 1, any neighborhood of 1 will have points outside the set. See here, when you're taking here means these points may lie outside. So this set is not going to be an open set. Next set is I equal to closed interval 0, 1 is closed. So we want to prove that this is closed. So how to prove? We should take a point outside your I. That is, this is the real line is given. And my point is 0. This is 1. Here is minus 1. So I want to prove that this closed interval 0, 1 is closed. So take a point y not in I. So this is my point y, which does not belong to this point. That means y can have this side or this side also. Suppose the first case I am taking y lying in outside. That is, you take y that does not belong to closed interval 0, 1. Then either my y should be less than 0, right? Or my y should be greater than 1. Either this side or this side it will lie. Now suppose I am taking y to be as y is less than 0. So what we want to prove, it is closed, right? So y is less than 0 means I can have y this side. You take the distance between y and 0. So distance between y and 0. So what should be the distance between y and 0? I will get this as y, right? 0 minus y will come. So I will get this as y. So this distance is 1. You take y by 2. So take d equal to y by 2. So where should it lie? Y by 2 here may come or here also. Now this will form an epsilon neighborhood of this y, right? So I have got an epsilon neighborhood of y which completely contain outside of this set. So whenever for this y I have considered this set is a closed set. In the same way, if we are taking y greater than 1, our y should lie here. So again I can go for the distance between 1 and this y. So in this case, distance between, that is if y greater than 1, distance between y and 1. What is that value? Y minus 1, right? Now you take y minus d as, suppose this I am taking d1, this is d2 as y minus 1 by 2. So y minus 1 means up to here, right? This distance. By 2 means this distance. From here to here I can go for this y minus 1 by 2 distance. I can consider an epsilon neighborhood here, right? So in this case also we can say that closed interval 0, 1 is a closed set. Now the last example, the set H equal to 0 less than or equal to x less than 1 is neither open nor closed. That means take your real line, the point 0, here is the point 1, here I am taking as minus 1. So my point is this is included and this 1 is excluded, right? Now this set is not going to be an open set. First of all, it is not open. What's the reason? Reason is that when you take the point as 0, any neighborhood of 0 will contain points outside of this set, right? So this is not open. Again, it is not closed. It is not closed. What's the reason? We can take the point 1. Okay, if you are taking the point 1, any neighborhood of this point, 1 is not a point here. Suppose my H I have marked as this closed interval 0, 1. Now 1 is not a point in H, but any neighborhood of this 1 will have non-empty intersection with this set. But for any epsilon greater than 0, some epsilon neighborhood of 1 will have non-empty intersection with our set H. But according to our definition, in order to show that this is a closed set, it should have empty intersection. But we are getting non-empty intersection. So this is not going to be a closed set also. It is not open, not closed. Now here is an example, an empty set. is open in R. When you are taking this empty set, it is open. What is the reason? Because it does not contain any point. By our definition, for every x belongs to this set, there should exist an epsilon neighborhood. But here, in empty set, there exists no points at all. So we can trivially assume that there exists an epsilon neighborhood also. So in this case, it's very trivial. Also, the set is closed. The set is also closed since its complement is R, which is open. That was our first example. In your first example, we have shown that R is open. So this empty set is empty set is either open or closed. So we have got empty set as open and closed. And here we have got one set as 0, 1, which is neither open nor closed. Right? So these two are important because we used to say that opposites, right? When you are taking open, we will say that its opposite is going to be closed. But in real analysis, it is not the case. That is, we can have, see, this set is open, also it is closed. This set is neither open nor closed. This is not open, so we cannot assume that not open does not imply that it is closed. See here, it is not open, but we cannot say that this is closed. This is not closed also. So be clear with this idea. That is, not open does not imply that the set is closed. So in today's class, we have seen the definition of a neighborhood, then definition of open sets, definition of closed set, how to show that a given set is an open set, how to show that a given set is a closed set, and we have seen some examples also. So with this, I am winding up the session here. Thank you for your patient listening. Thank you.